All right. Nice to be here. The summit is always a great experience at the high point of the year. So, I like to give an overview of what's been happening in TS, and this is sort of the main points of what we're doing with LionsOS, Microkit, sDDF, our verification agenda, what we do with Pancake, and the new topic, device interface specs, and some other stuff. And I'm trying to be not too repetitive with last year, not to bore people, but also there's a lot of stuff to pack in anyway. So, starting with LionsOS, which includes the work on Microkit and sDDF, although they are notionally separate, right? Microkit you can use without using any of the other stuff. sDDF you can use without using Microkit or LionsOS, it is independent. So, just a quick recap. I introduced LionsOS last year, but not everyone was there, and people's memory, certainly mine, it wouldn't be good enough to remember everything. So just sort of the high level is that it's a new operating system built from scratch on top of SEL4, based on this principle which I call radical simplicity. So we really go out of our way to keep things as simple as possible. And there's two reasons behind that. A, we want to be able to do that in a uni research group, so can't be a huge engineering project, but really the core reason is we want to prove all this stuff correct, and therefore simplicity is really the core enabler. And so we really try to take seriously what we teach first-year students, but usually never observed, certainly in the operating system space. Very fine-grained modularity, strict separation of concerns, all the good stuff. On top of that, a strictly event-driven, purely sequential programming model, and this is what's imposed by Microkit for exactly those reasons of making things simple and verifiable. So just this design already helps to get things right, and we actually do notice that we can develop things relatively quickly. People spend very little time debugging even complex stuff like device drivers, etc. But of course, in the end, it will really help verification, because verification scales purely with complexity. There's been work that shows, done by Gavin and collaborators, his students, that the verification effort grows with the square of the size of the specification of a module. So that's a very good incentive to keeping things simple. The strictly sequential code may be upsetting to some people because, well, the world is multi-core. Our claim is if we keep the components really simple, then it's not necessarily to have multi-threaded code. We can get the concurrency by distributing the modules over the cores, and that's basically the approach we do. And the other real driver for simplicity is this notion of use case specific policies. And this is really, I make no claim this model will work for general purpose computing. I do make the claim it will work for embedded systems, because in an embedded system you should really know and understand your use case, and you should know and understand what are the right policies, resource management policies for that use case, and that you implement in a single model as simple as possible. So we get use case diversity by making the policies very easy to swap out. And we demonstrated that we can even do that at runtime, although I don't really think that is necessary. So that's the principle behind it. And how does it look like? So we have SEL4 at the bottom, of course. And then we have an abstraction of the very complex SEL4 API, and that's been mentioned before, the complexity of SEL4, it's just very hard to use. And so the Microkit abstracts the complex API into something that's vastly simpler. And it's an abstraction in the formal sense, that the SEL4 API is actually a refinement of the Microkit API, and we've had some proof of that for an earlier version. And then on top of the Microkit, but as I said, not tied to the Microkit, is the SEL4 device driver framework, the sDDF. And on top of that, we build operating system services, and that's our LionsOS. And I'll give you an example of how it works. So we have a networking subsystem. It has a network card at the right end, And then we have a device driver that operates this network card, and its one and only one job is to translate the hardware-specific device interface to a hardware-independent device class interface. So basically at the operating system side, it presents a generic Ethernet card without any of the ugly details. And then we have, the driver has only a single client, and that's a important part of the simplification. Its clients are virtualizers. In the case of Ethernet, we can keep the transmit and receive paths separate, so there's two of them, and one handling receive traffic, the other transmit traffic. And so they share the virtual device between multiple clients, and also do address-based translation and cache management, etc., where it's needed. And then the transmit virtualizer, this is one case of a resource management policy. So if your clients overload the capacity of the network card, then you need a policy to determine which takes preference. And that's encapsulated in this transmit virtualizer, and it's nowhere else. And then there's a may or may not be a separate component for handling broadcast requests. There may or may not be copiers to keep the client address spaces separate. That's whether you have those depends on the security policy of your system. They're completely transparent. You can plug them in or pull them out. The rest of the system doesn't care. And then we have the clients. You notice there's no IP stack in the general system. The IP stack becomes a client library. So it's no longer part of the trusted computing base of the system. And each client has its own copy. And the client can be virtual machines. That's completely transparent to the rest of the system. So, very strict separation of concerns, really taken to the extreme. And an example of this is the web server. Last year at the summit, we launched the web server on SEO4, of the SEO4 website on LionsOS. And this is what the structure looks like. So there's about a dozen components, and most of them are trusted. And they're small, they're single-threaded, they communicate via asynchronous shared memory-based communication, zero copy as much as possible, and they're location transparent. So each of these components is associated with one particular core, but the rest of the system doesn't know which core that is. So a component doesn't know whether the component talks to us on the same core or a different one, and they can migrate, and that will be important for core management. And this is what it looks like in detail. So these are all the components in the system. The reddish ones are the untrusted ones, so there's a fair bit of code, hundreds of thousands of lines. But the trusted bits is 3,500 lines across 13 modules. So average 270 lines per module. So this is really very small, verification friendly. And incidentally, the whole trusted computing base of the system is about the size of the Linux device driver for that platform, the Linux Ethernet driver for that platform. So our Ethernet driver is 400 lines of code, so about almost an order of magnitude smaller. Now, all the green stuff here is written from scratch because we want to verify it, we want to really keep it simple and clean. But of course, you can't expect everyone to rewrite all the drivers for their devices, so there needs to be a way to reuse existing drivers, and we have a setup that does that, where we can use unmodified Linux drivers in our system transparently. The way it works is we use for every driver, doesn't have to be, but normally that's a setup. For every driver, we have a separate driver VM, which runs a stripped-down Linux kernel that contains this driver. And on top of that, we have an application that uses the Linux UIO for user IO framework to talk to that driver. So there's an application in there that basically controls the driver by doing Linux system calls. And that is then has a memory mapped, a memory region that is then shared with the rest of the system. And the important thing is the interface to the rest of the system looks exactly the same as for native driver. So we can plug in these Linux driver VMs transparently, and the rest of the system doesn't notice anything, except, of course, performance will be worse. And part of that is to support the signaling protocols we need. So the LionsOS sDDF drivers use SCO4 notifications to communicate, and that all gets forwarded by appropriate hooks in the Linux kernel, in the virtual memory management unit. Virtual machine monitor, sorry. So the important thing is, at the interface to sDDF, it just looks like a native driver. And the setup needs to be a certain amount of setup, of course. This is common to all devices in a particular device class. So you need to do this setup of the Linux VM, the driver VM, in particular this UIO driver, only once per device class. The effort, this shows the memory cost of this. So by default, it's pretty big, 100 megabytes. But with a little bit of work, it can be stripped down to a couple dozen, to a dozen or 2 megabytes per driver VM. Normally, as I said, we keep all Linux drivers in separate driver VMs, but we could co-locate them as well if you're really memory paranoid. Effort, few days to set up the UIO driver. This is once per device class. That's not a lot of work. And a total of 2 weeks for optimizing it a bit. Now, admittedly, these are Peter Chubb weeks, so multiply by a factor of 2 maybe for more models, but it's very little effort per device class, and then you can get every Linux driver in that device class for free. Incidentally, the same setup, that's not yet released, but we're working on it. The same setup can be used to develop LionsOS components in Linux. So you can use all the Linux development framework to develop your LionsOS component, and when it's done, you migrate it into native LionsOS, and it just works. It will. Once it's, as I said, this is at the moment a student project, but it will happen in the near future. So, the status is a fair bit has happened since last year. So Microkit is now available for ARM and RISC-V. We do have a graphics editor for doing the system design, describing the architecture, etc. And we support GDB debugging as well as profiling. So it approximates a real development environment. We have x86 support closed emerging, and that includes support for the CapDL loader. So in the near future, we will completely use the CapDL loader as for loading Microkit-based systems, and this should be sufficient for closing the RFC, I would think. Yes, Gavin is nodding. So this should come within the next few weeks. Multi-kernel support, our inspector friends keep beating up on us on this one. It's coming. I've been promised a demo version by the end of this month, so that's not too far away. It will take a bit more time to mature it, but it's going to be here soon. We're also working on and offline in cores, so this requires migrating components between cores, and the main thing that's holding that back is it requires kernel changes. The SCL4 kernel at the moment has no notion of a core going away or joining and reinitializing, so that's the main challenge there. But it's work in progress, and we've got an excellent student working on that one. And the other thing is that will probably take a year or so is template PDs. So this is allowing a degree of dynamism in Microkit. So Microkit has this static architecture where we have to, at system configuration time, you have to decide what components you have, what PDs, and what connections between them, their channels. And that's not going to change, but we looking at this as a mandatory access control. So in the sDDF, you basically specify the maximum rights, access rights for communication and shared memory access. And then we are overlaying that one with a discretionary access control that restricts what the mandatory access control allows. So the idea there is to have a special signed section in an ELF file that contains capabilities to the specific connections that are allowed for this executable. And when the ELF file is loaded into the protection domain, a trusted loader checks which capabilities are there and will blow away any connections that are authorized by the architecture but not by the executable. And from talking to various people, including our friend here from Lincoln Labs, I'm convinced that this degree of dynamism is what we need in embedded systems. I don't see a need for more than that. I think any use case I've seen so far will be covered with this. That was Microkit. sDDF drivers, we now have a significant and rapidly growing class of device classes that are fully specified and have at least one working driver. So for each of these, you have the specs, you have a template for at least one platform, which is easy to adapt to other platforms. We're writing new drivers all the time. So that includes all the easy stuff, serial timer clock. PinMux was a bit more complicated, I2C SPI, Ethernet, of course, storage, and an RFC, an NFC card reader. In addition, we have driver VMs, so there we also have device classes specified, but no native drivers, but we have the setup for Linux driver reuse, and this includes two-dimensional video, graphics, sorry, Ethernet. We doubled up there. We have native, but we can also use Linux Ethernet. That was mostly for demonstration purposes because these Ethernet drivers are really easy to write. Storage, sound, and video capture is in progress. All these have implementations on at least one ARM board, and a subset exists for x86 and RISC-V. We do write drivers normally in C or Pancake. You can also write drivers in Rust. We have a few Rust fanatics. For example, there's a storage driver written in Rust that's transparent to the rest of the system. And in particular, compared to a year ago, we have broken the dependency of sDDF on Microkit. So as long as your OS environment supports similar kind of very primitive abstractions, basically wrapping notifications and protected procedure calls, then you can use sDDF drivers in your system. And in terms of the rest of LionsOS, the kind of services we have at the moment, networking, of course, which uses what we call the native LionsOS API is always asynchronous because that's best performance. You can layer an asynchronous POSIX-like API easily over that asynchronous high-performance API. We haven't done that for networking, but we've done it for storage. So storage we support with the native asynchronous API as well as with the POSIX-like blocking API. We have debugging support, profiling, and multi-core is working fine on the SMP kernel, and as soon as multi-kernel support is provided in the Microkit, that will be pretty much available there as well. As a matter of fact, the Microkit really abstracts away between the difference between multi-core and multi-kernel. So that's a good thing in that respect as well. And things in progress, very imminent is x86. The main thing there is I/O, MMU, and virtualization support. So Microkit has x86 almost there. For LionsOS, there's still more work to be done, in particular the VMMs. and as I said, multi-kernel support. Now, performance was mentioned yesterday, and actually today as well, that yeah, just for having the safety of a microkernel, you just have to sacrifice a bit of performance. That's actually not true if you do it right. So I've shown some performance data last year already. Meanwhile, they have improved further. So this is networking throughput on single core ARM. So on the x-axis, we apply a varying load. And on the y-axis, we measure how much throughput we actually achieve. So we send data in, the system echoes it back, and we measure how much we get back. Green line is LionsOS, yellow line is Linux. And you see Linux tops out on this gigabit network at about 500 bits per second. So megabits per second, so about half the NIC load. Why? If we look at CPU use, we see that's the dashed line. Yellow is Linux again. We see Linux tops out the CPU at about half the maximum load, and then it can't handle anymore. Whereas SEO for LionsOS manages the whole thing with about a third of the CPU capacity to spare. So we beat Linux roughly by about a factor of 3 in performance. Why? Because just we execute less code. That's basically the story. This graph compares the cycles per data, and it's a factor of 1.8 to 3, where we just execute fewer cycles to do the same amount of useful work. Linux just does a lot of useless work. CPU load is not the only measure people are interested in networking. The other is latency, and the story here is similar. Latency, this is a logarithmic graph. The dashed lines are latency figures for Linux and LionsOS, and we are between a factor of 3 and 10 faster in network latency than Linux is. This is pretty astonishing, actually. I was amazed when I saw those data numbers. This was all single core. How about multi-core? Same story, pretty much. Linux does a bit better on multi-core, but actually not that much, and we still beat it hands down. You can see on this multi-core configuration, SEO, the LionsOS system use about 80% of a CPU all up. Before it was about 65%. So overall usage has gone up. This is a reflection that cross-core communication is more expensive than intra-core communication, but still the system nicely distributes and makes really good use of the multi-core. Same for x86, pretty much the same story. We beat Linux hands down. We ran the systems benchmark, so this is client scalability. So far, we always had a single client that was handling data. How does this change? If there's multiple clients, the overload gets distributed over multiple clients, and we see this here. Well, there is a effect. Distributing the load between multiple clients takes more effort to do, so the CPU usage goes up, but it's still pretty moderate. We can handle about 10 clients easily without CPU blowing out. Storage, similar story. So this is on a SanDisk, so a solid state device. Read performance, sequential on the left, random access on the right, and again, green is LionsOS, yellow is Linux. The solid lines are throughput, and the dotted lines are CPU utilization, and we see throughout we get slightly more throughput than Linux at dramatically less CPU utilization. Very nice performance. So this was read performance, write performance, similar story. We just get slightly better throughput at dramatically less CPU use. Very efficient system. And we ran a macro benchmark, a web server, comparing LionsOS with Linux on with a NFS-based storage, so using NFS to access the data on a backend store, versus in-memory, so the tall lines are using NFS to go across the network, and the lower bars are using a local in-memory file system. And if you look at the error bars, there's no difference between the SCL4 and the Linux performance. So it's totally at par. So in that sense, it is a performant operating system for real-world use. Cool. So if anyone ever comes to you again, talk about performance being an issue on microkernels, call bullshit right away, or call me. Other things. We've got a firewall project, so contrary to what Robbie was talking about, this is not an embedded firewall, this is meant to be a standalone firewall. And eventually I hope this to protect the SCL4.systems website, ideally the UNSW website, but I don't think I'll get that past the bureaucracy. But at least the school website, I think we should be able to protect that way. So it's a firewall. I'm not going to go into a lot of detail. The main thing you can see here, lots of components. There's about 24 different components in the system, and it's still very rudimentary. So what it does at the moment is TCP connection tracking. It handles a few protocols. It has a very rudimentary GUI via web server and some basic routing. What we really would like to do is sort of extend that into a really full-blown web server firewall. And for this reason, we are launching this as a community project. So as of this morning, if you go to this website, LionsOS docs examples firewall, you will find this page, which describes the firewall system, and we are basically inviting the community to provide the functional, the missing functionality in this project, and we hope that this gets taken up. We've already did a dry run with some visiting students from a US university that were there for about a week and added functionality to the firewall, which showed it's actually usable, approachable. It doesn't take all that much to install this system and get going. So I hope people will do it. So that's LionsOS. The next thing is what we're doing in verification. And there we have a verification agenda which basically says verify LionsOS plus a few other things. So a bit more detail, and this is a collaboration with Plan 5, a Munich-based RISC-V design house, and funded mostly by Cyberagentur, is verifying first pretty much our trusted computing base in LionsOS. And you'll hear about from Junming particularly how we're doing this. In particular, we want to have a complete solid verification story for device drivers, and I'll talk about that a little bit more. And we want to, and this is what our Plan 5 partners are doing, verify critical modules in the hardware, including the fence.t instruction, which is being developed at ETH Zurich for RISC-V processor. That is the core mechanism we need for preventing timing channels. And we want to be able to prove that we can confine an untrusted component, stop it from leaking data, including via timing channels. And we also want to have a strong real-time story for mixed criticality systems. So that's a pretty ambitious plan. Notionally, we're supposed to deliver that by about 2 years, pretty much 2 years from now. Chances are parts will slip, but that's reality. We found that, okay, some things were actually easier than we thought, some things are harder as we knew. It's research after all. So, but it won't take all that much longer. Part of that is, okay, we have components which we want to verify. So there is a specification, and then there is a refinement proof for that particular component. And there's many of those. And some of them are device drivers. And then there's the question, okay, where do we get the specification for the device driver from? And I'll talk about that later. And then, of course, there's a story how to fold that into overall systems properties and verify those. And Matt has talked about the criterion approach for this earlier. Junming will talk about what our plans are for doing both the component verification, or what we're already doing for the component verification, and what the plans are for the system property verifications. And the other thing is, well, underneath is SEL4, and a complete story requires that we connect these component verifications to the actual SEL4 spec. And apparently nothing like that has ever been done before. And this is one of the things Tom is working on. And he will give you a presentation right after this on the plans for connecting the user level proofs to the SEL4 spec. Last time I talked a fair bit about time protection, which is really a core part of this overall agenda. So proving the absence of information leakage via microarchitectural timing channels. I'm not going to go into much detail, it would take me too much time. Just what we are actually working on right now. This project has been dormant for quite a while. It's been rebooted a year ago with the Cyber funding and making good progress. On the system side, what we're doing is the old model of time protection was pretty much useless except for a very narrow class of systems because it did not allow any communication at all between components. And so we're turning that into a usable system model where we can have overt communication channels and still being able to prove that there's no covert communication channels, neither in the same direction as the overt channel, nor importantly, of course, any back channels. And the first step is to have a proper model for the system to actually do that, and the second is making sure it actually works. So this is where we're working on playing with these models and doing evaluations on channels and see whether our defenses actually work, and then this will be part of the verification story. And the other thing, of course, is that the verification itself is progressing. We are in the process of redoing the refinement from the abstract model to the C implementation, the first refinement step to the executable model. No, the first step is the abstract invariants, which are mostly done, and so the rest I couldn't judge, but I trust my verification experts, in particular Rob Seisen, who is responsible for that, and he thinks it's all under control. So this is looking good. So that's one thing, well, just a quick status update. Another thing is SEL4 was the only protected mode operating system kernel with a sound and complete worst case execution time analysis. And Tom was very intimately involved in this project in the days when he was a PhD student, and we had this sort of complex tool chain, or still a fair bit of complexity, that basically analyzes a program binary, gets information fed in from the verification at the C code level, and from that extracts in the end a worst case execution time for every possible code path through the kernel. This has been done at the time, it's now about 10 years ago that we did this work, and it was all done for 32-bit ARM pre-MCS. A much simpler kernel at the time, and only 32-bit, and because these things are in the end all state space explorations, the word size actually matters. We have now restarted this project about early this year using a new tool. Part of the problem was that by the time we were halfway through this project, the tool we used was unsupported, and it was all very hacky and sticky-tabby. We now use a new tool called Heptane, which was developed at INRIA and the French University, and that's sort of supported still. And we use that turned out it was a lot of work required to make it actually work on a kernel, because these tools tend to be just designed for analyzing simple control code at user level and have no notions of functions not returning and stuff like that. So that's been implemented. It had very rudimentary RISC-V support. We now have support for everything we need in RISC-V, full 64-bit, and it groks the MCS kernel. So we now have, again, a live worst-case execution time analysis of the kernel that's actually maintainable. The actual results we get out of it at the moment are sort of fantasy values, because we just put in placeholder instruction latencies. So, but if you have a platform for which you know the latencies, you can plug them in and get a proper sound worst-case execution time analysis of the kernel. The medium-term goal is to not just read latencies out of spec sheets, but extract them from the hardware implementation. And this is again where we're working closely with our colleagues at Plan 5 in Munich. It's their job to give us the latencies out of the actual hardware implementation. And that will make a really sound story for worst-case execution time. Next topic, Pancake. There really is a lot going on in TS. So Pancake is meant to be the main tool for verifying device drivers. Why is verifying device drivers a particular challenge? So SEL4 was expensive to verify, but that was justified because it was a one-off, right? It's a highly reusable artifact. Device drivers are just the opposite. They're commodities. You buy a new board, you get new devices, you need a new driver, and if you want to have verification story, you have to verify a new driver. So this only works with a scalable, repeatable process. And one of the things is, for device drivers, of course, they're very low-leveled, and they need a low-level systems language, something that has the right constructs for dealing directly with hardware, as you have it in C. You don't have that in Rust either, for example. That's where you have to break out into unsafe constructs, etc. We want to do everything inside the language. And one of the things we learned from the verification, the SEL4 verification project, is there was a lot of work required just to deal with the shortcomings of the C language, the undefined behaviors, etc., the poorly defined semantics and all that. And so our approach to making this a problem tractable is first simplify the problem by simplifying the device drivers. And of course, this is what our sDDF is designed for. It really radically simplifies device drivers. But then the other thing is to have a more suitable systems language, which has a well-defined semantics and but no gimmicks, basically. And automate as much as possible. And part of that is having a verified compiler, but also using automatic verification tools. And so our language for this, which I introduced, or was introduced last year already, is Pancake. So Pancake is a very low level, even more low level than C language, that reuses the KML compiler stack. So the right column here is the KML compiler. KML was the second language ever with a verified compiler. It's an ML dialect, so very high level garbage collector and all that sort of stuff we don't want to have in our operating system. And its compiler is basically written in HO4 as about 50 rewrite rules through about 24 intermediate languages. And with Pancake, we tap into the lower third or so of this compiler stack, add a few more intermediate languages and the compiler passes, and voila, we have our verified Pancake compiler, and it exists. So we do have a verified compiler for Pancake, which means that whatever we prove at the Pancake semantics level will hold at the binary. And so progress since last year. More functionality, so we now have directly 16-bit and 32-bit load stores in the language. Before that, we needed foreign function calls for that. We now have global variables, which makes life much easier in writing real programs. And we have shape checking, which is sort of poor man's type checking, in the sense that at least it distinguished between a word and a struct. Turns out systems people don't really like fancy type systems, but they would actually have a little bit more of a type system, at least something that distinguishes between an integer and a pointer. So probably that will come at some stage. At the moment, we just do shape checking. There's other usability aspects. Basically, we shared memory. Oh, forgot to mention that there is support directly for accessing shared memory. So that's device registers as well as DMA memory or shared buffers between the rest of the operating system. And so that's all supported natively in the language now. As a result, we need very few foreign function calls anymore. At the moment, it's mostly the memory coherence operations which still need foreign function calls. And they limit the performance. A year ago, we had about 100% overhead over C. Now it's 15 to 20%, and it's dominated by the remaining FFIs. So if you have a barrier instruction, you need an FFI for that instruction. To the instruction latency, the FFI adds about 30, 40 cycles. So that's quite significant. So just having that integrated will remove most of the overhead. And my saying has always been, if the overhead is 10% or less, I don't give a damn. And so we'll get there soon. We have a student who got really keen on this and rewritten almost all the drivers for the Max board. So we have now a fairly complete set of Pancake drivers for this Max board. And the student is also in the process of rewriting libmicrokit. So the implementation of this abstraction that Microkit offers over the SEO4 API. And that will make it easier to re-verify it. Things that are in progress. Function inlining is mostly there. This is close to merging. There's general more compiler optimizations. In particular, memcopy is at the moment, everything is copied bytewise. That's a waste. Decompilation of the logic, so we can use interactive theorem provers to reason about Pancake programs at a more abstract level. Hoare logic. Ask Junming what that involves. She will talk about it. And also verified transpiler, which also will occur in Junming's talk. Okay, that was Pancake. I mentioned earlier that driver verification is more than just verifying the logic of a component. Why? We've done a study about 15 years ago, same year as SEO4 was published actually, on device driver bugs in Linux. And the student really analyzed pretty much hundreds of bug reports for Linux, as long as they related to device drivers, and found that this is the breakdown of driver bugs. So we have the gray is concurrency errors. We eliminate those almost completely by design in the sDDF. And the rest we can deal with by verification. So we basically knocked out that group. The reddish one is OS protocol violations. So this is the device driver not correctly communicating with the rest of the operating system. And this one is the core of what we're doing with device driver verification in Pancake at the moment. So that's what Junming will be talking about. Then the green ones are generic errors, which basically means just normal programming errors, overflowing variables, pointers addressed out of range, etc. And a lot of that is eliminated already by Pancake, and the rest is again covered by verification. And so that leaves the elephant in the room, which happens to be the biggest group. 38% of the faults are device protocol violations. So device protocol violations really means you misunderstand the specification of the device, or the specification of the device is wrong, or the specification is right but the implementation is wrong. So you basically drive the hardware incorrectly. And that's a dominating source of bugs. So we can really only claim we have a handle on verifying device drivers if we solve that group. And this is very active project at the moment, again, close collaboration with Plan 5, where we take a device implementation in Verilog, and which is a finite state machine representation, and translate at the moment manually this in Hall 4. And that is then a deep embedding of the Verilog code in Hall 4. And Hall 4 has a thing called, or is it KML? I don't remember well. Our verification people will know more about it. It has a verified export of this into an abstract syntax tree in Hall 4. And from the abstract syntax tree, it also has a verified pretty printer, which can be used to produce Verilog. So then we can produce a verified Verilog representation of this Hall 4 finite state machine. And there's tools that allow to do an equivalence check between these representations in Verilog. And if we have this, then we know that the FSM prime Verilog at the bottom right is actually a refinement of our finite state machine in Hall 4, our deep embedding. And then there is work on doing a verified device Verilog generation from that. And then the idea is we use interactive theorem proving to derive the actual formal specification of the device in Hall 4. You can't let hardware designers loose on Hall 4. They will run away from you very quickly. But this is no longer what the hardware people have to touch. This is then in the verification domain, and we can then pull it up to the right abstraction level we need to verify our Pancake drivers, and then this will be done by the process described by Junming in the next talk. Will that work? Well, we've got most of it working already. So this is the status for I2C, where we have mostly either done or close to being done the whole chain from the device spec in Hall 4 down to the device Verilog. So it's just engineering from now on, so we know this process works. We are also done most of that for another device, SPI, and we're going to next tackle an actual Ethernet controller. A real-world Ethernet controller that's actually used in certified security critical devices. At the moment, that's still a cumbersome process using a lot of manual intervention. The idea is that we want to simplify this into an automated process where we use decompilation to go from a deep embedding to a shallow embedding, and then just the remaining lot of interactive theorem proving to go from the shallow embedding to the actual high-level device spec. And again, I have to trust my verification expert on this, but they are confident that we'll pull that off in the next 2 years and probably faster than that. And this is really then key to properly eliminating device drivers as a safety or security problem in the operating system. It's going to be a major. Quick rundown on other work. We just started a new project funding by Air Force Research Labs on secure microservices on SCO4. I noticed that the Kernkonzept Barkhausen people have just published a paper in OSDI on that channel area. So they're taking the bang away from us a little bit, but we have some ideas on how to do that better, and of course you always learn from the previous work. So the idea is to provide microservices. We don't aim for OSI compliance or OCI compliance, but we will have shared and read-only shared and partitioned writable file systems, and this will make heavy use of the PD template idea I talked about earlier. So this really will force us to implement that. And the other thing, Alvin talked about that at the last summit, the general purpose provably secure OS, which now has a name, it's called Javula. That's been pretty dormant for a while. We just rebooted that one. There's 4 postgrad students working on this one, so this will really accelerate. So, to wrap up, performance isn't a weakness, it's a strength. So as I said, if someone makes claims to the contrary, call bullshit. It's just not true. What it really comes down is using the right design and really careful implementations, and then it's no issue. And really, if you think about it, if you look at how many cycles are needed to process an incoming network packet and deliver it to the client, Linux uses about 20,000 or so. Which is excessive, as we've seen. But compared to the cost of context switches, which are about 400 cycles each, that's huge, right? So just doing a back-end of the envelope calculation shows you that the microkernel overhead should be negligible, it should be in the noise, and we've shown that it actually is. The other important point is device driver availability is no longer limiting factor. We can reuse unmodified Linux device drivers in the LionsOS system or any system that uses the sDDF. And that's very powerful, of course. At the moment, for a limited number of device classes, but as I said, it's a couple weeks' work to add a device class once we specified it in sDDF. So that's really no longer a bottleneck. Our system services are maturing. I wouldn't say it's a mature system yet, but it can run real-world systems for sure. And Junming will explain how we do the verification of user-level components. That's progressing really well at the moment. And we're really in the process of solving the device driver problem for good. And then the other thing is, yes, we're back in the hard real-time game. So SEO4 is once more the only protected mode real-time operating system kernel in the world with a sound worst-case execution time analysis. With that, thank you.
Hey, thanks, Gernot. Questions?
Thank you for the very nice talk. Yeah, okay. So the device model building framework that you described assumes that you have implementation of the Verilog for the device. Is that the case? Or
yes.
Okay, so I mean.
So the idea is we use existing device implementations. We're not in the business producing them, but there's plenty of open source ones around. At the moment, we're using mostly the ones used by the Pulp project at ETH Zurich, so Ariane, Cheshire, etc. Okay. In RISC-V, and for other platforms, there's other ones available.
I wonder what you do when you have a proprietary device and you only have documentation for that device and not the implementation. You can't solve.
We find a hardware guide to implement it.
Okay, I mean, and the problem of solving driver specs is harder than just building your own drivers and constructing specs from them, I think.
If you don't have the implementation of the device at hand, you cannot have a complete verification story. That's obvious, right?
Yeah.
So you can't have the one without the other. As far as we're concerned, we're only dealing with open source things. If you have a closed source device for which you want a verified driver, nothing is stopping you from using our framework to produce a specification for that, and then we can deliver the verified driver for you.
Yeah, that makes sense.
This will all be open sourced, right? It's most of it is happening in an open source environment anyway. The main thing is most of our funding comes from Cyberagentur, and they have tricky rules. We have to get approval for getting everything released, but part of the project promises is it will all be open source. And we push it out as quickly as we can. And in particular for the worst case execution time patches, where's Christian? Not here. Ah, here. When are we going to get the permission to feed that back? Okay.
Thanks. I mean, I'll yield, but I do have a follow-up question.
Okay, I'm so sorry to ask, but I'm still thinking about the performance claims with regard to the network driver. Is it really impossible to saturate a gigabit NIC with the IMX8 platform using Linux, or is there a specific set of configuration?
We tried very hard. And we have a lot of Linux know-how in the team, right? And no one ever, we put this data out there, right? They've been out there for a year. No one ever challenged us on the Linux performance claims.
Unless this is someone else. Okay. This is just I guess a small question. At the beginning of the talk, you said something like, we're going to remove concurrency from all of these small modules. But the complexity goes somewhere, right? It goes to the system level.
Yes, I didn't talk about this because I talked about it last year. Nothing happened since then. We do use model checking to verify the signaling protocols between those things. So the concurrency control in the system happens in two places. The one is there's all these shared queues, and where everything is based on very simple, bounded, single producer, single consumer queues. Okay. They're very easy to get right. The concurrency control is simply in the enqueue and dequeue functions, and they're strictly three-liners. And we actually have a PhD student who is a total weak memory nerd who is going to verify that these are done correctly. And the other thing is the protocols for signaling. A producer needs to signal the consumer when there's data in the queue, etc. And it's very easy to implement these very inefficiently. If you try to optimize them, you run into deadlocks very quickly, as we found. And we found model checking is very effective for eliminating that. Right now, the model checking is done in Spin using a Promella model that's completely separate from the C code. I've got a student working on a validator that checks that the Promella model is actually consistent with the C code. That's not a proof, but it's a good assurance.
That's a model of the system level concurrency, or the?
That's a model of the intercomponent concurrency, just as far as the notifications are concerned. So you signal and wait for semaphores, and that's what the model contains.
Okay, no, that makes sense. I mean, the SPSC implementation is probably not the.
And I mean, there's the overall system-wide properties. That is also a concurrency problem, and this is what Junming will talk about, what the plans are for that.
Thank you. Thanks.
Any other questions? Oh.
You talked a bit about the sort of your approach to dynamic systems with the template protection domains. Will that appear on your verification agenda at some point?
So in terms of the security model, the mandatory access control is given by the architecture, and yes, we'll plan to have a verification story for that one. Overlaying that with a discretionary access control really comes down to the trusted loader. So I expect eventually we want to verify that this one does its job correctly. It's not on the roadmap right now.
Any other questions? Okay, thank you, Gernot, and we have a 30-minute break now.